Hi everyone. So today I would like to provide a high-level overview of one of my papers. The name of the papers, as you see, it is on the screen, a Unified Association Methods to Leverage Multiband Capabilities in 6G Networks. This paper is in the second round of review at IEEE Transactions on Wireless Communications. So I will not go over the implementation details or the equations, just an idea about how the algorithm works and the theorem that is covered in this paper. So imagine that there is a city where there are three types of routes. A slow one, but it is very reliable, and this is equivalent to sub 6 gigahertz frequency. And then there is a slightly faster route, which is equivalent to the millimeter wave. And then a super fast route, but it is fragile, very fragile. And this is equivalent to the terahertz band. So most people will always choose the slow route because it never breaks. It is very reliable, even though that there are faster routes which are empty, underutilized, and they can carry much more traffic. So this paper argues that this happens because the current systems decide things in pieces. So they first choose or pick the road, and then they decide how to share resources or how to share space on that road. So once that early choice is finalized, everything else will be stuck with it. So this naturally pushes all the flow, all the users towards the slow, reliable road, which is the sub 6 gigahertz band. So my algorithm does that in a smarter way. So it decides everything all at the same time. So it decides the users that will be chosen for allocation, the base stations, the frequency bands. On top of that, keeps in mind also the mobility and the blockage probability. Okay. So which base station and frequency band to use? Okay. So to make this practical, the big problem will be split into smaller parts using something called dual decomposition. These smaller parts, they talk to each other and they still agree on a global decision. So on top of that, the system will learn over time which roads or which paths will likely get blocked using an online learning system. So the paper develops a theorem which is that under mobility and blockage and system blockage, the coupled decomposition means that, as I said, everything is decided independently, or we can call it also decoupled optimization. So decoupled optimization is strictly suboptimal compared to coupled or joint optimization, even when each decoupled stage is optimally solved. Okay, so let me show a certain video, a certain visualization. So this is the opening scene. Let me stop for a while because the video will go faster than my speed. Okay, so in this opening scene, as you can see, the simulation will start with the joint optimization mode. And it is shown with this, you can see there is a label or a green indicator on the right. So this is 6G. The network here is a 6G multiband network. We have 6 base stations arranged in the grid. There are 2 red circles. They represent the sub-6 gigahertz. There are 2 blue ones. They represent the millimeter wave. And the purple ones, they represent the teragigahertz, which have the radius of the covering circle is the smallest in this case. And then, of course, here it is assumed as 120. And at the beginning, you can see several types of users. The colored dots, which are scattered throughout, these are the users. The green ones, they are EMBB, or Enhanced Mobile Broadband users. You can see 10 of them. And these users care more about speed. So they're speed sensitive, like, for example, video streaming, as an example. The yellow users, or the yellow dots, they are for URLLC, which are ultra reliable low latency. And these users care more about the time. Okay, so they are very time sensitive, and they are for critical applications which are time sensitive. And then also after that, there are other users which are for massive machine type communications. So those lines, these thin lines that are connecting users to base stations, are the links or the active associations. So this is the joint mode. And in this mode, you can observe how users are distributed across all the 3 types of bands. And you notice also, if you look at the labels, I hope you can see it, sub 6 gigahertz now, like about six users are associated to these base stations. These base stations usually have the strongest power. And then other users as well are associated to the other 2 types. So there is a kind of balance here. Okay, it's a balanced distribution. No base station or no band is taking more users. So all 3 bands are being utilized, nothing is underutilized. Okay, let's continue with the video. Let's move forward a little bit. As you see, as the simulation goes, we can see that there are more users are joining. More users are getting associated to the millimeter. You can see here, several users are associated to the millimeter wave base station, others to the gigahertz or the sub 6 gigahertz. So there is balance. You can see here also. Let me stop the video for some time. Okay, so we can see here, like, there is still balance, despite we can see that more blockage events are happening. Okay, so we can see here, even with increasing number of users and blockage events, the optimization problem, or the joint, or we can call it the coupled optimization, still maintains balance. Okay, and you can notice also that the load percentages on base stations is even. Okay, like, for example, the top one, or the top sub 6 gigahertz station, shows about 100% load with 10 users. The millimeter waves are also, they have about 30% load serving. And also, like, the sub 6, the terahertz also, it has adequate load. The total throughput here has increased right now. Okay, let's move forward the video to the critical moment when the mode switches. Now you can see here mode is about to switch. Yeah, see here. Let me stop here and let's analyze what is going on. Okay, so you can see here the mode started switching. It switched to decoupled optimization. So what happens immediately here? So we can see here that there is a dramatic visual change that took place. So almost, you can see here, almost every connection now turns red. And it's pointing towards the sub 6 gigahertz base stations. So this is the bias we are talking about. This is the sub 6 gigahertz bias in action. And user association dynamics or distribution changes significantly. So now more users will start to join the sub 6 gigahertz base station, and the other ones will uh, get less users. And as the simulation continues, we'll notice that towards the end, there will almost be no users in the millimeter wave or the terahertz band base stations. Also, we will notice that the blockage events have accumulated so much, they keep increasing. And the algorithm here simply connects the user to the strongest signal, which is obviously the sub 6 gigahertz, because it has better propagation characteristics. Okay. And we may notice also that as the simulation continues, that there is an uneven load distribution. We'll notice that the top sub 6 gigahertz base stations will have like 100% of the load. As I said, the other ones will be underutilized. And even that the data rate is showing a high data rate, but this is actually deceptive because the links are blocked. Users are not getting good quality signals. Okay. So that's the algorithm. As I said, I try to maintain simple explanation without going into implementation details. And I will try to post another video where I will go over the equations and explain everything. This paper is currently, as I said, under the second round of review. We provided like point by point reply to the reviewer comments, and we have high expectations for this manuscript, given the time and effort we spent on this paper. And thank you so much for watching my video. I appreciate if you would like and comment on my video. Thank you. Have a good day.